welcome back. Today I am going to start a topic on polymer solution, but let me just recap what we did last time. So, yes, in the last lecture, we went through the derivation of Van Laer theory, okay, where we described the derivation of basically excess Gibbs free energy. And then later we showed that the activity is represented in this form. Okay, these are the forms for Ln gamma 1 and gamma 2 for a binary liquid solution, where A dash is related to the van der Waal equation of state parameters A's and B's. Okay. Then we talked about Scatard-Hildebrand theory, which basically depends on the same set of assumptions, which is basically a regular solution theory, where the S axis and V axis is going to be 0. In that case, Scatard-Hildebrand tried to avoid the use of van der Waal equation of state, and using cohesive energy density, it came up with an expression of Ga in this form. Okay. And this they introduced the volume fraction as well beside the cohesive energy density, and in that case it turned out to be that ln of gamma 1 is related to this, where it's a volume molar volume fraction, and the difference in solubility of the different liquids which is related to the cohesive energy density. And this regular solution equation based on this theory can be related to the van der Waal equation by considering A dash in this form and B dash in this form. Okay. Now, this was what we covered. Now, we are going to just look at polymer solution. Okay. I will not go too much details in that, but just to give a flavor of that, the theory which we looked into is all physical in nature, and the polymer solution later on we will be describing the Fleury-Huggins theory. It is based on the latticed concepts. However, I will not go to the derivations and rather assert the equations, but let me just describe what is a typical polymer, or what is the typical properties of polymer. Okay. So, if you look at polymer and compare with typical solution or typical solvent, you would see that the polymers are typically made of various different chain, which can be linear or which can be branched, right. So, a typical property is basically these polymers are chain molecules, okay, and this can be linear, branched. Now, when the branch react together, the cross linking occurs in the polymer. Okay. Then you can have a homopolymer, where all repeat units are same. Okay. Then you have copolymer, where you have at least 2 or more different repeat unit. Okay. Then you have these dendrimers, which are hyper branch tree like structure. Now, the size of the polymer plays a significant role in the properties of the solution, and essentially typical properties such as typical forces such as dispersion and Hutchins bonding in such case plays a significant role, and it basically governs the thermophysical property of the polymeric solutions. So, the size plays a big role. Okay, now these polymers can exhibit different kind of structures also. So, polymer exhibit different structure, but it has limited tendency to crystallize. Now, usually 30 to power 80% limited crystallinity is possible only if the molecules have regular structure. So usually that means that most of the time the polymers are amorphous in nature. Okay. Now, usually the polymer melt over a temperature range. It's not like it doesn't. It has a it instantaneously melt at a specific temperature. Usually it has some range of the temperature. So polymer melts over temperature. Okay. So the range could be 10 to 20 degrees Celsius, and the reported value of Tm, the usual reported value of Tm refers to highest temperature of the melting range. Okay. The other important thing is that the melts of non-crystalline or crystallizable polymer, if you cool it, then it can take a glass structure at glass temperature, which is called Tg. Okay. So let me just draw typical specific volume versus temperature. Okay, and let's assume this case. A typical way, if you consider usual solution, then this may be the case with the specific volume as you decrease the temperature, and it drops at typical freezing temperature, attains usually the crystalline state. Okay. So that's a usual liquid, but in case of the polymer, you would see a little different scenario. So it may have same system behavior like this. Okay, so this is let's say liquid, and you are quenching it and reducing the temperature, and at this point it can change the slope. Okay, and this change in the slope basically indicative of glass temperature, and this is basically nothing but glassy state. Okay. Now it depends on the rate at which you are quenching it. So for example, if you quench in a different way, it may happen that it occurs somewhere here. Okay. So that means you can have different glass temperature depending on the quench rate. Now typically this is the liquid, and at this point it will be something like a rubbery state. Okay. So let me just give the salient features of this different state. So well below Tg, amorphous polymer usually are are hard, stiff and glassy. Okay. So, it need not be not necessarily brittle. Okay. Now, well above Tg, the amorphous polymer they are rubbery or plastic. Okay. That means there is large deformation is possible. Okay. Now, if you consider synthetic polymer, synthetic polymers are usually polydisperse. So, they are polydisperse okay. And how do you measure this dispersivity? By considering average molecular weight, let us say MP, which is going to be summation Ni Mi divided by summation Ni, where Ni is the number of molecules with molecular weight Mi. Okay. Or you can consider weight average molecular weight, which is going to be something like this, Mi square divided by summation Ni Mi. Okay. So, and polydispersivity sometimes is also called heterogeneity index. Is given by MW average and N average. Okay, so or MP average. So, here Ni is again, this is the number of molecules with molecular weight Mi. Okay. Now, this polydispersivity index typically is in the range of 1.5 to 2.0. Okay. So, that is about a brief description of the polymeric system. So, what about the theory for polymeric solutions? A popular theory is basically given by Fleury-Higgins theory, which is based on the lattice models. Okay. So, what are the assumptions for this? So, the Fleury and Higgins they have taken the assumption as follows. The first important assumption is basically that the system is athermal. So, that means solution is athermal. So, essentially that it is deviating from the typical discussion we had last time, where we Van Laar or scattered Hilbert solutions. That is regular solution theory, where basically the excess entropy is also considered to be 0, but here in this case for Fleury-Higgins the assumption is only athermal solution, and the other important assumption is that the polymer behaves like a chain of monomers, that is as if it consisted of mobile segment each about the same size as that of the solvent. As solvent molecules. Okay, so which essentially means that whatever the size of the solvent molecule, the monomers of the polymer have the same size. So that becomes easy for doing all the analysis. Okay, so let us consider N1 as number of moles of solvent, N2 is number of moles of polymer solute, okay, and let us say R is number of segment in a polymer molecules. Okay. So, given this, what is the number of monomers? So, that will be N1 plus R times N2, and this is number of moles. So, we multiply by Avogadro number. So, that would be the case of total number of monomers. Now, for simplicity, we also defined volume fraction. So, that would be 1 N1 plus N1 L and 2, putting star to, and this is phi 2 N1 plus R and 2. Okay. So, this is the definition of volume fraction. Okay. Note that each monomer has same size, and that is why it should be straightforward. Okay. So, now what does Flory-Huygens theory says? So, it says that S E by R minus is basically nothing but minus of x1 ln phi 1 star divided by x1 minus x2 ln phi 2 star divided by x2. So, that is what Flory-Huygens theory says as far as the excess entropy is considered, and this you can derive it using the lattice model, considering that the polymer occupies the lattice points of the space, but we will not go through the derivation of this. Okay. We just asserting this expression. Okay. Now, you can also rewrite in terms of mole fraction. You can also rewrite this expression replacing x1 in terms of R. Okay. So, since x1 is n1 times, you can also consider x1 in terms of this moles. Okay. And you can simplify this expression and bring the R, which is the number of segments in the polymer solute. So, if you do that without showing the detailed analysis, I am just writing the expression here. Minus x2 ln R minus phi 1 R minus 1. Okay. So, this is the expression. Now, we know that this is athermal solution as far as the Flory-Huygens theory is considered. So, Gx by RT is Hx by R T minus Xx by R, which is nothing but minus Sx by R. Okay. So, now you have the handle to Gx. So this is same as this. Okay. So given this, that you have this Gx, in terms of minus, this would be your you know, this would be your nothing but x1 ln 1 minus phi 2 star 1 minus r plus x2 ln r minus phi 1 r minus 1. Okay. Now for r greater than 1, okay, you can do the analysis. Gx by rt is less than 0. This is imply this is a negative deviation from the Rawls law. Okay. So this is different from what basically the regular solution theory talks about. Okay. For the case of non-athermal or basically thermal solution, where basically your Hex is not equal to 0, you can add a van der Waal or Scatchard-Hindlebrandt term to Gx. Okay. So let me just write down here, for non-athermal solution, it is basically customary to add a Van Laar or Scatchard Hildebrandt term. So in that case, your Ge or RT is okay. So I can use the earlier term here, which was this, right? So G by RT is x1 plus phi 1 x1 plus x2 ln phi 2 divided by x2, right? So I'm going to use that. And now since it's athermal, so this is basically nothing but your minus of Sx by R. Now for athermal, I'm going to add this term, okay. So this is due to the Van Laar Scatchard Hindlebrandt term. Okay, so in this case, this chi parameter is called Fleury interaction parameter and is determined by the intermolecular forces. So this is related to the intermolecular forces, okay, approximately omega by kT, determined okay, where omega is basically nothing but exchange energy between solvent molecule and the polymer segment. Okay. So now given that you have this G of x available, you can obtain the activity as we have done in the earlier case. So of course I have not gone through the derivation in details, but something which you can directly use it in order to solve the polymer solution problems. So I'm going to write down the solvent activity coefficient in this case. Activity coefficient is given by ln gamma 1 is ln 1 minus phi 2 1 minus r plus phi 2 star 1 minus 1 by r plus chi phi 2 star. Okay. So, this is the solvent activity coefficient. Now, if you would like to see how this is going to be affected by the segment length, we can actually directly use this for a given some chi parameter. So, this is typically the behavior of ln gamma 1 as a function of phi 2 for different r values. So, this is for the case of athermal when we consider chi to be 0. Okay. So, when you consider athermal solution, you will see something like this. Okay, where r increases along with that. Okay, for the case of this would be corresponding to r infinity. Now, you can consider another case where you have again ln gamma 1 with phi 2, okay, where r is infinity in the sense that it is infinitely long chain, and then we are going to consider different chi. So, this is around, this was around 0, this is around 0, and we are going to get something like this. So, it is not perfectly in scale, but this is something where the chi in this case is 0.5, and this is reducing here, this is somewhere is 0, and then chi can be negative also. In that case, for example, chi could be in this case 0.5. Okay. So, you see it is not changing much as far as the overall nature is concerned, okay, but it is relevant that to understand that it has a significant effect on the activity values. Particularly, it also depends on this. If you see here the volume fraction, okay, of the polymeric solute, okay, in this case. But again, the point of description of this thing was to just to illustrate the changes it will have typically, and the more details you can get into some book. The test book has more detailed information on it, and the idea was not to get too much of details within this course, but to illustrate what you would like to do if you have a polymeric solution and how to solve a simple problems. So, if you are interested to get into more of this, you should look at chapter 8 of the test book, where figure, let us say 8.6, 8.7 illustrate the use of Flory-Higgins theories to explain activity coefficients of heptane and polyethylene solution, and similarly for other cases. Okay. Now, I will consider a specific case now. So, let us consider R infinity. In that case, log of gamma 1, the activity of this solvent, can be reduced okay. So, in this case R is infinity, then you have ln gamma 1 is ln 1 minus phi 2 star plus phi 2 plus chi phi 2 star. Okay. Now, this further can be simplified, okay, and I can write this as ln phi 1 plus phi 2 plus chi phi 2 square. Okay. So, this would mean that ln gamma 1 minus ln phi 1 star minus phi 2 star is chi phi 2 star. Okay, and now I can divide this phi 2 here. This means that ln gamma 1 minus ln phi 1 star minus phi 2 star divided by phi 2 is nothing but chi phi 2 star. Now, this is something which we can compare with the Scatchard-Hindelburg theory. So, if you compare with Scatchard-Hildebrand theory, then you can find that chi. So, if you arrange it and then you compare with the Scatchard-Hindelburg theory, we find that chi is nothing but V1 by RT, the difference in solubility to the square, okay, where we know this V1 is nothing but the molar volume of the solvent, okay, 1, and delta 1 and delta 2 are the solubility parameter of solvent and polymer respectively. So, this is something which is a beautiful way to obtain the chi parameter of Fleury's interaction parameter using the molar volume and solubility parameter of the solvent and polymer solute. Okay. So, for good solvent, usually the chi parameter is less than or equal to 0. Now, since chi using this is related to this, which essentially means for a good solvent your solubility of solvent and the polymer should be all same order. Okay. Now, this parameter which we have obtained here or written here is rather empirical. Okay. So, note that Fleury parameter is empirical. Okay, and if you try to find out this chi from a polymer concentration and a polymer size dependent, or if you try to find out the chi based on the neutron scattering and from calorimetry, it will find to be different. And so, usually these are not consistent, and chi essentially is dependent on the polymer solution or polymer concentration and is also polymer size dependent. So, chi is usually dependent on some polymeric concentration and polymer size. Okay. So, in spite of that, there is a limitation as far as the Fleury-Huygens theory is concerned. There is a large usage of such a theory for solution, polymeric solution, and thus is very popular. Okay. Now, if you are interested to find out immiscibility, so if you are interested in polymer solvent immiscibility, okay, then the polymer or the using this Fleury-Huygens theory, you can only obtain partial immiscibility. So, Fleury-Huygens theory can only explain partial immiscibility of a polymer solution system at low T. Okay. So, it requires chi to be greater than 0. So, you can do the same analysis as we have done for earlier to find out the immiscibility. You look at the second derivative of G of or delta G mix. So, let us do that. So, if you find out this should be less than 0, which essentially means chi should be greater than or equal to 1 by 2 1 by r to the square. So, incipient instability, that means when it is equal, occurs at chi is equal to 1 by 2 1. So, this should be plus 1 by square. So, in that case the corresponding critical solution, or sorry, critical composition, corresponding critical composition phi 2 C is 1 by 1 root of r. Okay. So, this comes directly from this analysis. So, let me make just last few comments. If you put r equal to 1, if you note here, if you put r equal to 1, this will give us the same analysis as done for Margulis equation. Now, recall that chi parameter which we have shown here is proportional to 1 by t. So, in that case the Floody-Huggins theory is associated with only the upper critical solution theory. Okay. So, it only predicts the upper critical solution theory, but in reality, so it predicts only upper critical solution upper critical solution temperature. So, Floody-Huggins theory is associated with an upper critical solution temperature, that means it predicts only the one such case, but if in reality you might see different kind of critical solution temperature. So, for example, you can have this where this is LCST, this is UCST, this is 2 phase, this is 2 phase and this is 1 phase, and this is a function of T versus solvent segment fraction of polymer. The other case where you can have something like this is 2 phase, this is 1 phase, and you can have something like this also, it's closed, this is LCST, this is UCST, 2 phase and this is 1 phase. Okay. Again this is T versus solvent or segment fraction. Okay. Now, these are the case which is for binary polymer solution, and this is something which tells you that for such a scenario the Floody-Huggins theory does not work very well, because Floody-Huggins theory is associated with only upper critical solution temperature. Now, so this was kind of a brief introduction of the polymer solution. Particularly we introduced the Floody-Huggins theory, which was based on which is based on lattice model, and this will be the end of the liquid solution or theories for the solutions. What I am going to do in the next lecture is basically take up few examples to illustrate how to solve such a problem using the activity models. So, I will see you in the next lecture, and that will be the last lecture of this particular course. So, see you there.